So welcome to discussion number 6. And so in today's discussion, we'll just mainly do some exercises about op-amp, diode circuit, and also the MOSFETs. So basically, all of today's discussion will just be exercises. So hopefully we can finish 4 problems today. Okay, so here's the first one is a textbook problems of op-amp. So this one is op-amp problem, where we want you to solve this op-amp. So in this, you can just, I will give you 1 minute to just read through these problems, and then I will start to working on it. So this one, just from this one, this figure, we can find is an inverting op-amp. So I think some of you may still have question about how to decide is inverting amplifier or non-inverting amplifier. So inverting amplifier, we mean if the input is directly connected to the negative terminal, then it's called inverting op-amp. If the input is connected to the plus terminal, the positive terminal, is called non-inverting op-amp. So that's how we define inverting and the non-inverting. So as long as you have an input connected to the minus terminal, this is a non-inverting op-amp. And for this one, we assume this is an ideal op-amp, right? So the gain of the inverting op-amp, the gain of inverting op-amp will just be negative R2 over R1. This is for if we just have resistance. Well, in this op-amp, this circuit, we have a capacitance as well as resistance. So we cannot use R2 over R1 for our ratio. In this case, we'll use negative Z2 over Z1. We will, with Z be the impedance in the loop. So for ideal op-amp, in the inverting configuration, the gain is always negative Z2 over Z1, with Z2 be the impedance of this part, and Z1 is the total impedance of these two elements. So that's how we define Z2 and Z1. And the impedance of resistance is always itself, but the impedance of capacitance will be J omega C inverse or SC inverse. That's the impedance of resistance and capacitance. So to find what's the gain of this closed loop or inverting op-amp, we have to find what's Z2 and Z1 first. So Z2, so the Z2 part is actually a C2 in parallel with R2, right? That's the total impedance of this feedback part. We'll just C2 and R2 in parallel. And we can just plug in the impedance of each element. So for the C2, the impedance will just be 1 over J omega times C2 in parallel with R2. This will give us J omega C2 plus R2 inverse. That will be the total impedance of Z2 part. Basically, you just do the same equation as the two resistors in parallel, right? 1 over R1 plus 1 over R2, then take the inverse. This is a Z2. Well, Z1 is C1 and R1 in series. So it will just be J omega C1 inverse, that's the impedance of the capacitor, plus R1. This is your total Z1. Then the final gain, let's call it V out over VI or ACL. That's the final gain of this of this inverting configuration will just be negative Z2 over Z1. We just put the Z2 and Z1 into this equation, and we'll get negative 1 over R1 plus, oh, okay, I'll just solve it step by step. Will be negative Z2, which is J omega R2 C2 plus 1 and R2 over 1 over J omega C1 plus R1. Just solve this, you'll get V out over V1 equals to negative 1 over R1 plus 1 over SC1 times 1 over R2 plus SC2. Rearrange this, you'll get negative R2 over R1 over 1 plus, S equals to J omega for all this case. It'll be 1 plus 1 over SC1 R1 times 1 plus SC2 R2. So just calculate Z1 and Z2 separately, and your gain will just be the ratio of them, and then take the negative value. That's how we derive these equations. So let me so we have derived these equations so the difference between our previous result to this equation is basically you just need to replace S over with J omega. These two are the same for Laplace and Fourier transforms. So in case we have V out over Vi, this is our closed loop gain, our gain of this circuit, and we want to find we want to make the Bode plot when omega much less than omega 1. So just take a look at this equation. So when omega much less than omega 1, this part will be large, right? Because omega 1 over omega will be large. And also, I think this circuit had an assumption that omega 2 is much greater than omega 1. That means omega divided by omega 2 will be small in this case. So this equation can just be simplified as V out over Vi equals to negative R2 over R1 divided by 1 plus omega over J omega, omega 1 over J omega. So we can just ignore this part because 1 plus a really small number is just equals to 1. So that's how we simplify the circuit. So when omega much less than omega 1, our equation can be simplified into this. And for the second part, we want to find what's the equation when omega much less than omega 2 and much greater than omega 1. So in this case, still use this equation. Omega 1 over J omega will be small because our omega will be much larger than omega 1. While omega over omega 2 will also be small because our omega is much less than omega 2. So this is another small value. So it will be 1 plus a really small value times another 1 plus really small value. We can just think the denominator be 1. So our V out over Vi will just be simplified as minus R2 over R1 divided by 1 times 1, which is just negative R2 over R1. This is the second case. So you will have omega in between omega 1 and omega 2. The third case, we want to find what the equation will be if omega much greater than omega 2. So go back to the equation. If omega is much greater than omega 2, this one will be small. While this one, omega over omega 2 will be large. So this equation can be further simplified into negative R2 over R1 over 1 plus a small value equals 1. So it just be 1 plus J omega over omega 2. This is our equation in the third region. And then we can just plot this, right? We can do a plot of this. So this is V out over Vi, the magnitude of which is our gain in dB. And this is our omega. I'll do it in log scale, just our omega. So when omega less than omega 1, we can simplify this equation, rewrite this one This equals to L times j omega on both sides. This will just be minus j omega times R2 over R1 over j omega plus omega 1, right? And then I will divide it by omega 1 on both sides. I mean, both denominator and numerator will be negative j omega over omega 1 R2 over R1 over 1 plus j omega over omega 1. This looks quite similar, right, to what we learned. So just by looking this, we have a pole at omega 1. And also we'll have a 0 because we also have a j omega in the denominator, right? If we have a j omega in the denominator, that means we have a pole, we have a 0. So in the first case, we have a pole at omega 1, but we also have a 0 starting from 0. So we have a 0 in BC, start from BC already. So what's the first part looks like in the Bode plot? So a 0 means plus 20 dB per decade. A pole means minus 20 dB per decade. So that's just in the first part. We'll have a pole start from 0. So at 0, we already have positive 20 dB per decade. This is caused by the pole. We'll have this positive slope until omega 1, because at omega 1, we are still starting to have the pole. The pole starts at omega 1, right? So we have a plus 20 dB per decade and also a minus 20 dB per decade at omega 1. So these two are just cancel with each other. We'll just have a 0 slope. This is how it looks like. And this matches with our second part, right? Because at the second part, when omega is between omega 1 and omega 2, we have a constant value. These two matches, right? We have a constant gain. There will be no zeros or poles between these two regions until omega 2. We just have a constant. Well, for the third case, for omega greater than omega 2, looking at this, there's no 0 in the denominator, no j omega in the numerator, so no 0. Well, we have 1 j omega in the denominator. That means we have a pole, which at omega 2. So starting from omega 2, we'll have a pole. We'll have a negative 20 dB per decade slope. So we'll have a negative 20 dB per decade starting from omega 2. So this is how we draw the Bode plot. And this is how the Bode plots look like for this circuit. Okay, we finished this part. And then move on. The last part of this problem is to design the circuit. So we want to design the circuit with gain of 40 dB and also low frequency 3 dB points and at 200 hertz and a high 3 dB free points at 200 kHz. Also the input resistance of 2K ohms. Let's solve this one by one. First, the gain of this op-amp of this circuit will be negative Z2 over Z1. And then we can go back. What's the maximum gain of this circuit? The maximum gain happens at here, right? At this region, that's the maximum gain happen, which with the gain value to be negative R2 over R1. This is a maximum gain we can get, constant. So if we want a gain of 40 dB at the middle frequency range, that means our negative R2 over R1 will be 40 dB. 40 dB is 100. So we must have a ratio, take the magnitude. So the ratio of R2 and R1 must be 100. This is what we can know from the 40 dB requirement. The second requirement is F1 equals to 200 hertz. And F1 is a lower frequency 3 dB point. Let's come back to there. And our assumption is omega 2 greater than omega 1. That means the lower frequency 3 dB point will be omega 1. So that means F1 will equals to omega 1 divided by 2 pi. And our omega 1 is 1 over RC. So from the low frequency 3 dB point, we can find what's the value of R1 and C1, the product. The high frequency 3 dB point, which is F2 equals to 200 kHz, and F2 will equals to omega 2 divided by 2 pi. This will give us 1 over R2 C2 times 2 pi. Yeah, you just need to know the omega for RC circuit for cutoff frequency is 1 over RC. That's the definition. So 3 requirements, we have 3 equations, but we still need 1 more to solve the actual values of R1, R2. We'll go back to check the last one. So the input resistance at omega 1 greater than much greater than omega much greater than omega 1 is 2k ohms. So what's the input resistance? To find the input resistance, first we have to open the output. As you have learned in lecture, we have to open the output. And then we give a test voltage Vx at the input. We want to find what's the Ix. And then our Rin, the input, will, sorry. And our Rin will just be Vx divided by Ix. So that's how we solve the input resistance. Okay, let's solve this. First, if we give a Vx, so Vi equals to Vx here, what's the current? This is because this is an ideal op-amp. That means virtual ground always the same. So if you have a 0 volts at plus, we'll always have a 0 volts at minus for ideal op-amps. So what's the current? The current Ix will just be Vx minus 0 volts divided by R1. That'll be the current at this branch. So what's your Rin? Rin will just be Vx divided by Ix, which equals to R1. Sorry, it should be Vx minus 0 volts over R1 plus 1 over j omega C1. I forgot the capacitance. That means your Rin will just be R1 plus 1 over j omega C1. However, we have a requirement. So this is when omega much greater than omega 1. So in that case, the j omega C1 inverse will be small because we have a large omega. So the denominator is large. If we take the inverse, it's small. So we can just say our Rin at this frequency range will just close to R1, so which equals to 2k ohms. So then the problem is solved. We have R1 equals 2k ohms. We have the ratios of R1, R2. Also, we have 4 equations to solve 4 values. This is doable. So just by using this 4, we can solve R1, R2, and C1, C2. I'll put the result here. So our R1 is 2k ohm. Our R2 is 200k ohms. You solve this. C1 is 0.4 microfarads. C2 is 4 picofarads. So this problem is solved just by following the steps. Next one, this is quite similar to what you have done in the past homework. So in the past homework, you also have 2 diodes, but I think your diodes is in this direction instead of what I'm showing here. These 2 are quite similar, right? So we the input we give is a square wave input, something like this. This is the input we gave. It has a period T with peak 1 volts, minus 1 volts. This is the input we gave. And do we want to know what's the output waveform should be? Okay, I'll just start because I think you have saw this in the homework. So first, let's consider the region where first I will say sorry, I forgot to mention what's the diode looks like. So this is how the diode looks like. This is the diode circuit. This is the diode circuit, and this is the current. This is the voltage. The diode is turned on at 0.7 volts. So when the voltage across the diode is 0.7 volts is turned on, and with a vertical line showing its current. So it's an ideal diode with turn on voltage 0.7. So for this one, let's first start to solve this. I'll first consider this region, so the positive region. When Vs is greater than 0, I'll first consider this region. So if we have a positive Vs here, our voltage at this point should be negative, right? Because if you take the gain, right, the gain of this op-amp is A V times V plus minus V minus, but you have a positive signal at minus terminal. If you take the V plus minus V minus, will give us a negative value, times A is another negative value. So you will have a negative output at this point. So positive Vs will give you, let's say this Va, will gives you a negative Va. You just think of this. So if you have negative Va here, this diode will be turned on, right? Because it will have positive, it had negative on the N side. So D1 is on. However, for D2, it has negative in the P region is off. D2 is off. That means we can just ignore this. This is an open circuit. We have open circuit for D2. So the circuit will just be, you have a Vs here, you'll just have a current and it will flowing through 10K ohms and then to the output and also to the ground. This is how the circuit looks like, how the current flows, which is just inverting configuration you have saw in all the lectures. So what's the gain of this configuration of this circuit? It would just be V out over Vs will just be negative R2 over R1, which is negative 5. So our output, it will be something like this. So your V out will be, right now we have 1 volt here, we'll have a negative 5 volts here. So this is what the output will be if we have a positive Vs. And for the second region, if we have Vs less than 0, I mean, we consider this part, we have Vs less than 0. Erase all this. So if we have a Vs less than 0, we have a negative here. Then our output will AV times V plus minus V minus will be positive. So we have a positive VA. Here is still VA. That means we'll have positive for diode D1, we'll have a positive on the N side. So D1 will be off. And D2 will be on. Sorry, D2 will be on. So it's different. So we have a D2 short circuit here. So for this Vs, if we have Vs, we'll have a current flowing through R1, and we have a short circuit at D2 because when the diode is on, the current is infinity. We just have a vertical line directly to the infinity. That's the ideal diode. What ideal diode will happen? So if we have a current flowing through R1, then all of the current will just flowing through the diode. There will be no current flowing through R2. So in this case, we'll have so our V out will be V minus, that's the voltage at the negative terminal, V minus minus the I times R2. However, there will be no current flowing through R2, so the I will be 0. It will just be V minus. And because of the virtual ground of the ideal op-amp, our V minus is also 0. So for Vs less than 0, or for negative Vs, we'll have 0 volts output. So then we can just do it. That's how the output will look like. We'll have negative 5 volts, 0, negative 5 volts, 0, and move on. So this circuit is called precision rectifier. If you like, you can just Google it or rectifier or learn it in detail. This is called precision rectifier. It's pretty good to know this circuit. This is how we solve this. And The third problem, I'll give you like 10 seconds to read through this. It's PMOS. So we were solving NMOS before, but right now this is a PMOS transistor plot. Okay. Will not do this, so I'll just erase this. Nothing covered here. So first, I would like to first clarify is this an enhancement mode or depletion mode? So the definition for depletion mode transistor is this. So the transistor is on. The definition is the transistor is on even with 0 volts bias. So I will do a transistor here. This is a NMOS. PMOS. So we have a transistor here. This is a PMOS. Well, there will be current flowing through the transistor even with 0 volts bias. So even the gate voltage is 0 volts, we still have the current flowing through the MOSFET. In this case, the MOSFET is called depletion mode. And for the enhancement mode means to have a current flowing through the MOSFET or to have an on MOSFET, to make the MOSFET on, we must give it a non-zero bias voltage. So for PMOS, if we want to make this transistor have a current flowing through it, we must have a negative gate voltage. Or for NMOS, this is the NMOS. If we want to have a current flowing through it, we must give it a positive gate voltage. So the turn-on voltage of this two MOSFETs are different. So this is the definitions of enhancement mode and depletion mode. So depletion mode will have non-zero current even with 0 volts gate voltage. While enhancement mode will have a current only when the gate voltage is within or above a certain threshold. That's the definition of two different modes. Let's go back to this one. From this one, we can just say we have a non-zero, we have positive gate voltage. It's VSG. So okay, we have a negative gate voltage, and then we have a current. If we have a 0 gate voltage, we'll have no current. So I would say this MOSFET will just be enhancement mode. Because to have a current, we must apply a gate voltage to it. This is an enhancement mode transistor. This is the first we can solve from this plot. And then what's the value of Kp and VTP for this transistor? Okay, so we'll go back to what's the definition of Kp. So Kp equals to mu P C ox W over L. This is the definition. And the VTP is the turn-on voltage of this transistor. So to find this, I would like to find what's the saturation. I want to find what's the region of saturation and linear. So if you see here, I think starting from to the left of this point, this device is in the linear regime, and they start to saturate to the right of this voltage. So I would say this is the point where the transition from linear to saturation regime. And same, I would say this is a point where the transition occurs. And then if you do the plot, this side is linear regime, and this side is saturation. And we can say, at each of this point, is when saturation occurs when VDS equals to VSG minus VTP. This is where saturation occurs. So just by looking at using these 4 points, or you can just choose one of it, you can just solve it. So right, because let's choose this point. So this is when VSG equals to 5 volts. 5 volts minus VTP equals to, I'll say 4.2 volts. Then you can just solve your VTP, which is 0.8 volts. Pretty straightforward. And what's your KP? I'll prefer to use the saturation current in this line. So our saturation current is mu n C ox W over 2L times VSG minus VTP squared. And actually your VTP should be negative. It's negative 0.8 volts, but I just choose to use the magnitude here. So which equals to Kp divided by 2 times Vsg minus Vtp squared. I'll use this curve. So the current equals to 4,000 microamps equals to Kp divided by 2 times Vsg is 5 volts minus 0.8 volts squared. So you can just use this to solve your Kp. And your Kp is just 4.53 times 10 to the negative 4 with some units. This is what's Kp and VTP. And this is all we need for problem 3. Okay, the last one. The last problem is also a MOSFET. And you can see this is an NMOS. NMOS. From the symbol, we can just look at it. And we want to find the labeled node voltage. That means we want to find what's the V3, V4, and V5. What's the voltage of the 3 nodes? Another thing is of the circuit for all these 2 MOSFETs, the gate is directly connected to the drain. This is a gate, drain, and source. Gate, drain, and source. So the gate is always connected. It just connects to the drain. That means your gate voltage equals to your drain voltage. So that means your VDS will just equals to VGS for both MOSFETs to have the same drain and gate voltage. That means if we recall the definitions for saturation and linear, so if we have VDS greater than VGS minus VTN for NMOS, that's in the saturation regime. If you have VDS less than VGS minus VTN, this is in the linear regime. And we have VDS equals to VGS, which must be greater than VGS minus VTN. So these 2 MOSFETs are in saturation regime. We have 2 MOSFETs in saturation regime. These 2 are all saturated. And then let's solve for it. First, I mean, you can just you can directly get V4 just by looking at this figure, because 1 volt, we have 1 volts, and in the upper side we can 1 volts here, 1 kilo ohms here. We have a same MOSFET. So this circuit or this figure is pretty symmetric. Just by viewing it, we'll know V4 equals to 0.5 volts, which is 5 volts divided by 2. We can just find V4 just by viewing it because this circuit is symmetric. And also and then we can use KVL to solve the V4 and V5 and V3. So let's start, I'll do KVL here. So starting from V4, we have a 2. I'll start here. Okay. So the current in this branch will be mu n C ox W over 2L times VGS minus VTN squared. This is a current in saturation MOSFET. Always this. And your VGS equals to VDS which is mu n Cox W over 2L times V4 minus V5 minus Vtn squared. And you have Vtn equals to 0.9 volts, you have V4 equals to 2.5 volts. So you just have one variables for the current equation. And Kn, we also have Kn prime W over L equals to 1.5 milliamps per volt square. And Kn prime is mu n Cox. So let's do the KVL. We'll have V5, the voltage here will be the current times 1 k ohm, will be 1 k ohms times the current I. And the current is mu n Cox W over 2L 1.6 volts minus V5 squared. So you have V5 equals to an equation of V5. You can just solve this equation. Just solve this second order equations, and you can get V5 equals to 0.66 volts just by solving this. V4 equals to 2.5. Then what's your V3? Because this figure is symmetric, right? So your V3 will just be V4 plus V4 minus V5. So you'll get 2.5 volts plus 2.5 volts minus 0.66 volts equals to 3.34 volts. So the problem is solved. This is a simple MOSFET circuit, and we can just solve it step by steps. Yeah, this is all the 4 exercises we'll cover for this lecture. And if you don't have any questions, you are free to leave. Or you still have 10 minutes left, you can ask anything about the lab 2 or pre-lab 3. Thanks.